guys, welcome to another tutorial today. Today what we are looking at is a compound rod, and we're not going to assume small angle approximation, because in a lot of problems you will assume the small angle, but in this example we're not going to do that. We're going to change it around a bit to make it more interesting. So as you can see here, this is our compound rod, and as you can see, what we're going to do now, we're going to draw the first part, which is the angular velocity. We're going to assume is this direction, angular velocity, which can also be written as theta dot, well basically it's equal to d theta by dt. Now for solving this problem, what we want to do, as you can see, the whole length of the thing is L. We're going to assume it's a compound rod. We're going to assume that it's a slender rod. I know we haven't drawn that. I've just drawn it as a rectangle to make it clear that it's not, to make it clear that it's a compound rod, not, you know, an ordinary pendulum. And again, we're not going to assume a small angle. Like we are not, because often in the examples we assume a small angle, which makes the problem easier. But we're not going to assume that. That should be sine of theta, sorry. We're going to do it properly. So we're not going to assume that. Anyway, for the first part, what we're going to do, we're going to label it, the parts of it. So we've got the pivot point here, like there, and we're going to call that O, and then we've got the end point here. Remember, there's no width to it. It's just we've done that to show that it's a compound rod, but it's actually a slender rod. But it does have a mass, and it has inertia. We'll call the end of it A, and then we'll call the center of mass point here. This is the center of mass. This should be in the center. It's not drawn to scale, but that center of mass point, where the weight comes from, where mg comes from, the force down here, this force down here, that should be coming down from the center of the rod. So length over 2 from the top and length over 2 from the bottom, and that's called G for the center of gravity. Now, what we want to do now, we want to start by, we're going to use vectors because there are 2 dimensions here. We're going to call it, and if you actually look at it, what we're going to do, actually we don't need to use vectors. We can actually define it. We can define it as x and y values. So we know that x of the end A, we're calling it, is equal to, if we look at trigonometry, it's just going to be, as you can see, the angle theta is just going to be this way down. Sorry, it's the horizontal force. So it's going to be horizontal. Sorry, so it's how far it is to A to there. So that's going to be length times by sine of theta, like that. And then for y of A, it's going to be length, it's minus length times by cosine of theta. It's just trigonometry. As we are resolving upwards, the rod is hanging downwards like this. And as you can see, it's, you know, that's theta. And then we've got the arrow this way for sine. So, yeah, with that, we've now got that for y. So, yeah, for the next part, basically what we want to do, we want to find the velocity as a function of theta. And to do that, all we have to do is use calculus. So we look at these here, and we're going to find xa dot, so x dot a, and to find the derivative of L sine of theta. Now, with that, what we need to do, we know it's going to be equal, well, L is a constant, so it's just going to be equal to L. Now, when you differentiate like this, when you differentiate sine of theta by dt, you need to use the chain rule. So it's going to be it's going to end up being, we know the derivative of sine is cosine. However, you have to times by theta as a function. Remember, theta is a function of time. We know that to be true. We know theta is a function of time. So if we want to work out what theta, if we want to basically do that, what we need to do, that's going to basically turn into L times by theta dot, because that's the chain rule, times by cosine of theta. And that there is the velocity at point A, the horizontal velocity at point A, in terms of theta as a function of t. Now, it's the same for y. For y, you got the same thing. Y is equal to minus L cos theta. So and we know the derivative of cos theta is minus sine of theta. So that's going to be a double minus, which is a positive. So it's going to be y of A dot, the first derivative, is equal to L theta sine of theta. Now, to make this simple, let's write it as a vector. It can be nicer to write these things as a vector. As you can see, there's two things in common, L theta and cos theta. Sorry, there's L and theta in common. So you can write it as, in this formula here, that we know R, not R, we know velocity as a vector is equal to L theta, and then in the vector form, it's going to be cos of theta for the x direction, and then sine of theta for the y direction. Remember, it's positive now because when you differentiate cosine of theta, it's negative cosine. But when you differentiate cosine of theta, that becomes negative sine of theta. But because there's a minus already there, it's a double negative, so it becomes positive sine of theta. That's a vector for the velocity of point A, which we're going to be needing. Now for the next part, if we can do the same thing for the acceleration, and we'll get the acceleration first before going forward. So the same thing, acceleration. We're going to differentiate this vector, which means we just differentiate the top part and the bottom part. That's all it means. That's all we do. When you differentiate a vector like that, all you're doing is differentiating each part in there by separately. It may actually be easier to differentiate them separately on their own, but actually no, we can do this. So we can do it like this. What we're going to do, we're going to do the chain rule. We're going to differentiate this part first, and then we're going to differentiate this part. This for the chain rule. Sorry, not the chain rule. Sorry, the product rule. I apologize. It's the it's the product rule. I apologize. Not the chain rule. So acceleration of point A is therefore equal to. We differentiate that the L theta dash part first, which is going to be equal to L theta dash dash. So the second derivative of theta with respect to time, times by this vector here, because this is the product rule. Sine of theta, like this. And plus L theta dash times by the derivative with respect to time of cos of theta sine of theta as a vector, like this. That's acceleration of A, which is therefore is going to equal L theta dash dash cosine of theta sine of theta plus L theta, and then in there it's going to be the same in the chain rule. It's going to be minus theta dash sine of theta, and in there the same, it's going to be theta dash cosine of theta, like this. Again, that's the chain rule. So you've got the expression now for acceleration, which this is the expression for the acceleration of point A, as you can see. And again, cosine of theta, the derivative of cosine of theta is just going to be negative sine of theta. But with respect to t, you do the chain rule, theta dash, same for the cosine part. And that can be simplified into this. So acceleration of point A is equal to, let's do it a bit lower to make it simpler. Acceleration of point A is equal to L theta dash dash cosine of theta sine of theta and then plus, you take the factor of theta out, which there's a factor of theta out, and you get it into L theta dash squared, and then inside there, remember, it's negative sine theta, and then cosine of theta. This is now the acceleration of it with respect to t of the point A. So it's very useful. It's very important to get to try and get good at calculus, the chain rule, the product rule. These things are going to come up a lot in dynamics, like a lot. And you're often going to be dealing with angles that are functions of time. it's not always going to just be simply one angle. It's going to be different dimensions. Anyway, well, now we have that. Now we have the motion of that. We have the motion of the end of it in terms of theta and that. We want to find out we want to know what is theta dash. This is an important question. We want to, how do we find that out? Well, when you have a bar like this, I'll draw it out again. It probably won't be a great drawing, but it's like this, right? Again, the mass is there, mg, and it's at an angle theta from the vertical line. So you've got this mass here of length L. It's length over 2 to the midpoint, remember? It's length over 2. Well, there's a very famous equation which is very important to use, which is, you might have seen it, which is the moment of inertia times by the angular acceleration is equal to the torque. This equation is very important to remember, and this is what we're going to need. Now, I'm not going to go into moment of inertia too much in this example. I'm just going to tell you some things. So the moment of inertia of a compound rod about its center. So the moment of inertia here about its center, like that. Which, I mean, again, moment of inertia is how hard it is. It's basically how hard it is to turn something, you know, to turn something around based on its mass and it's based on its mass and geometry. So moment of inertia is due to, it comes down to mass and the geometry, because certain shapes based on their mass and geometry are harder to turn than others. Anyway, we know that the moment of inertia around the center of mass, it's not very clear, around the center of mass of a compound rod, which is actually like this, because it's actually a thin rod, but it's got mass. You know, it's got mass throughout it, if that makes sense. Like the mass is going throughout it, if that makes sense. A uniform mass, but it's not a single point that we've been dealing with in the past. This is an actual geometry. We've just drawn it again as a rectangle to make it clear that it's a compound rod. You know, it's like a continuous mass rather than a point. But anyway, this is what the moment of inertia of that is. I mean, I'd be happy to go into another video and talk about moment of inertia and where it comes from and how to derive it for different geometries. But it's equal to 1/12 ml squared. Now, there's an important thing we need to use, which is called, we want to find out what it is about the pivot. You know, that's finding out, you know, from here. We want to know what it is from the pivot here. This is the pivot, you know, it's hanging from pivot, where that's G, that's O, and that's A. And to work that out, we need to use what we call the parallel axis theorem. And for parallel axis, basically what you have is we know therefore that of the pivot, we'll just call it I of P, to simplify things, which is that point there. It's that point there. Anyway, what we want to do is that is equal to the moment of inertia around the center point, like this, plus md squared, where d is the distance, basically that the pivot is from the center. And we know d, because the center's halfway through, is going to be L over 2, which basically means it's going to, let's just change this to make it simpler. That basically means we're going to have, let's put the values in, you know, the center of mass, moment of inertia around the center of mass, we know is 1/12 ml squared. And then we know plus mass times by L over 2 for D, L over 2, like this, squared. Okay, and what's that equal to? If we times it out, that's going to equal 1/12 ml squared plus ml squared over 4. And that, you know, we can do the work if you want, but that's just going to be equal to ml squared over 3. That's just, you know, just adding fractions. As you say, you know, they're both ml squared over they're both ml squared. You know, they're both basically, you know, of that. So we can collect those, and it's going to be ml squared over 3, and that is what the pivot is. So for the pivot, we know that's, let's see, let's go here. I've written a lot, haven't I? Right. Okay, so for the pivot, let's write this down. For the pivot is equal to ml squared over 3. And the next part is the torque. Now, if we're looking at this here, if we're going to assume that it's turning, you know, we're going to assume direction as anti-clockwise, again, where it's the angular velocity, which is equal to theta dot. Now, with that, since we know that the angle is theta, we have to use moments. We know it's L over 2, which is L over 2, to the centre of mass, which is of mg. And basically, if we want to get that, what we want to do, we want to find out this distance from the pivot point, based on the angle, to the G point. You know, it's from O to G, like that. You know what I mean? It's that distance, and we know that distance is going to be. I'm gonna write down. It's going to be L over 2 sine of theta. Now, because the gravity is pulling it this way. You see, it's pulling it the opposite way of the way that we've resolved it. Because like you resolved, you know, the way that we resolved it vertically for x and y. No, I'm sorry, for y. I mean, you know, you might have resolved it this way for x. You know, you might resolve it upwards for y, and then to the right for x. You also resolve the angle. You resolve, are we going to, you know, do anti-clockwise or clockwise? We have resolved it to be anti-clockwise, and that since gravity is pulling against that, here it's pulling it this way. Therefore, it's going to be the full moment of the torque is going to be equal to negative mg L over 2 sine of theta. And therefore, we can now get the full equation for it. That's the equation. Remember, I theta dash dash, and we know I is ml squared over 3 theta dash dash is equal to, and we know the torque now, which is minus mg L over 2 sine of theta. Oh, that's not very clear. I apologise. So yeah, you can see now we are now getting together the full torque equation. There it is. That's the full equation now. We've now related torque to angular acceleration, and that's a really important way. That you know, it's the moment of inertia, the angular acceleration, and the torque have now been connected, which is going to be really useful. What we're going to divide both sides by ml squared over 3. So that's going to be theta dash is equal to, and it's going to be now 3, because you're dividing, so it's going to be 3. It's going to be 3 over ml squared, like this, and then it's going to be times by minus mgl over 2 mg L over 2 sine of theta. And we can just cancel things out. We know m is going to cancel out. We know that one of the l's is going to cancel out. So you're actually going to be left with theta, the second derivative of theta with respect to time. So yeah, the second derivative of theta with respect to time is going to equal, therefore, let me just double check. Yeah, it's going to equal negative 3g over 2l times by sine of theta. Now, when you first see that looks like that looks quite like almost like an unsolvable differential equation, because you've got it looks non-linear, doesn't it? Because you see that the sine theta, you see the theta dash dash. The thing is, if you have damping, if you have any kind of air resistance or any kind of damping force, it will become basically unsolvable by normal methods. But there is actually, because when there's no air resistance, when there's no damping, no external forces, there's a little trick we can do. You know, we have d squared theta by dt squared. That's equal to theta dash dash, right? Now, I'm going to give you a little trick with the chain rule. The chain rule can be very useful in calculus. There's a little thing we can do. Watch this. D theta dot, so d, you know, the derivative of the angular velocity by dt. Remember theta dash is equal to the angular velocity, and that's not very good angular velocity, is it? It's equal to, like that, the angular velocity, but I need to rub that out. That times by d theta. Sorry, that's the wrong way around. I apologize. It should be if I rub that out like that, as you can see, that's going to equal the same thing, isn't it? The reason why is because we know that d squared theta by dt squared is equal to d theta dash by dt. You know the reason why, because that is equal to d angular velocity by dt. As you can see those there, can't you? You can see that that's equal. That they are equal, therefore, as you know, it's the same as d squared theta by dt squared. It's the same as d theta dash by dt, because theta dash is just the angular velocity. The same way that acceleration is equal to dv by dt, or the same way that acceleration is equal to dv by dt, or d squared r by dt squared. Not very clear, but you can see the point with that, hopefully. Let me draw that out. So with that, we can see this little identity here. Because look what happens when look at this here. Look what cancels out when they go together. If those two cancel out, you end up with just d theta by dt again, which is the original one. See, that's again d theta dash by dt is d squared theta by dt squared. So there's a little identity there. So therefore we can write it as. Let me write it here. We can write it as d theta dot by dt times by d theta by dt is equal to minus 3g over 2l sine of theta. Now I'm going to give you another little trick. We know that d theta by dt is equal to theta dash. So this whole expression can be rewritten into this format, into a really nice form. D theta dash by dt, theta dash is equal to minus 3g over 2l times by sine of theta. Suddenly, this now is all this now is a basically separation or separable differential equation. It's suddenly a very solvable differential equation. All we have to do now is just basically, sorry, it should be, I keep putting dt, I apologize, sorry, this is probably, sorry for confusing you, it should be theta. Hopefully that makes sense now. It should be theta. That makes it actually work. That's what it should actually be. See, when it's in that format now, it's solvable. You can actually solve that differential equation now. We can just isolate the variables. So, we get, let's get into this one first. We get theta dash d theta dash is equal to, and you can just times by d theta, times both sides by d theta, and you're going to get minus 3g by 2l sine of theta d theta. So now you've got those two, and all we have to do now is the integral between, we'll just do an integral of this, the integral now of theta dash d theta dash is equal to the negative integral of 3g over 2l of sine of theta d theta. There we go, got it in that format now. And when it comes down to integrating, we know the integral of theta dash there is just going to be theta squared over 2, So we're going to have theta dash squared over 2. And then for the other one, integral, it's going to be cosine. So it's going to be equal to 3g over 2l cosine of theta, and then plus the integration constant. So we've got in this format now, we've integrated it. Let's just sort out this c part. All we have to do is basically, we know at theta, we'll start at the initial angle it starts at. So when theta equals theta 0, since we're going to assume at time equals 0, the entire system starts from rest. So therefore, the initial angular velocity will be 0. It starts from rest. So with that, you can stick both those into the equation, which is 0 squared over 2, which equals 0, which equals cosine of theta is going to be 3g over 2l cosine of theta, the initial theta angle, add c, like that. And we can just solve that very easily by getting c is equal to minus 3g over 2l cosine of theta, the initial angle. And there you have c. So we get the final equation. Guys, so if we look at the next part now, so now we have those. We want to basically look at this now. We have the 3g minus 3g cosine of theta is 0, like this. So we want to write out the full form of it, and the full form we're going to have. Wait 1 second. Theta dash squared over 2 is equal to 3g over 2. And of course we have it in that form up there. Remember we have for the actual equation it's cosine of theta like that. And then for the actual other part it's cosine of theta is like that. So let me just write it down. Cosine of theta minus cosine of theta 0, and that is the equation now for the acceleration, the angular acceleration. Sorry, the angular velocity. We can simplify it a little bit with theta like that is equal to 3g over l. Should be 2l. Sorry, by the way, 2l like that over l cosine of theta minus cosine of theta 0, like this. And then that's the final formula we have for that now. We don't need to simplify it any further right now. Obviously, it's square rooted. The issue is that if you want to do the next integral, the only issue is that the d theta by dt is that the integral can't be done by normal methods. You know, so we're not able to do that. So if you want to integrate it again, however, and we know obviously what the angle, we know what the velocity point of A is. It's equal to L and theta dash cosine of theta, and then theta dash sine of theta. So we can basically substitute in the theta dash, and we get an equation of motion for the velocity of point A. If we substitute the theta dot into this equation here, L theta dot cosine of theta, theta dash sine of theta, you can get an equation from that. We would ideally want to get this as a function of time, but we would have to use numerical techniques to solve that integral, and we're not going to go through that today. But yeah, anyway, thanks for watching, and I'd be happy to do more rigid body dynamic problems. This is a very interesting part of mechanics to do, and I'd be happy to do more problems if you want. I mean, I don't mind writing out the integral quickly if you actually want to see the integral, the way the integral would look. I mean, I'll show you what the actual thing. So you actually have theta dash is equal to. We're just doing this here just to see like that. We're not actually going to solve this, so if you don't want to watch this, no worries. Just I would just recommend leaving the video. We're just going to be just seeing what happens, what it actually looks like when it's in the final form. Theta dash, and it's going to be cosine of theta minus cosine of theta dash. Sorry, cosine of theta dash, like this. Make sure it's an L. Square root, like that. And we know theta dash is equal to d theta by dt. The problem is this is very hard to solve because you basically get into this form where it's like you get into quite a hard form at the minute. You know, the form we're going to have it is going to be like. Let me write it out first. 1. It'd be the integral of 1 over 3g over L cosine of theta minus cosine of theta 0, the initial angle, like that, and then all on a square root like this. D theta is equal to the integral of t, sorry, not of t, of dt, which we know is just 1 in there. So that is the integral form you're going to get into if you want to get theta. However, that there is very hard to solve with normal methods. You'd have to use numerical methods, which is the only issue with that. However, it's good to put in that form, and you could use numerical methods therefore to get theta dash. Sorry, theta is a function of time. But yeah, I mean, rigid body dynamics. It's definitely worth looking into this topic. It's using a lot of mechanics, and you'll see it in a lot of areas. You'll see it if you want to get further into mechanics and do advanced mechanics. You really want to focus on this, because this is how you step from just working with particles points. You know, because inclined plane problem. There's so many problems you do in mechanics that are just focusing on a single point in space. But in reality, most things aren't like that. Most things are going to be complicated geometries. Most things have inertia. A single point isn't really going to have inertia. You know, because there's no angular velocity usually. It's when you have geometry, that's when you have inertia introduced. You have these shapes, these masses that are continuous, and it's not just single point mass. Things get a lot more complicated. But I'd be happy to do more of these videos. There's a lot of examples we could do. Obviously, the double pendulum, that's exciting. I could do that. The upright pendulum. There's a lot of things we could do. But yeah, thank you, and please consider subscribing. Thanks.